Hey everyone, and welcome to today's explainer. If you've ever found yourself wondering how on earth your brain manages the sheer volume of experiences you collect over a lifetime, well, you're in exactly the right place. We're going to dive straight into the fascinating physical life cycle of a memory. We'll trace it from the exact moment it's recorded in crisp, high definition, all the way to how it eventually gets edited down into this streamlined, kind of Wikipedia-style summary.
So, I want you to start by thinking about your oldest, most cherished memory. Let's say it's your 10th birthday party. Why is it that you can perfectly remember the feeling of the room, the joy, maybe exactly who was there, but you can't for the life of you remember the exact perceptual details of the event? Like, you probably don't remember the color of the cake, or the exact pattern on the wrapping paper, right? Is your memory just a faulty video camera losing pixels over time, or is it acting a bit more like a storyteller, intentionally pruning away the fluff to leave you with a core narrative? To figure that out, here's our roadmap for today's explainer. We're going to cover the myth of static memory, meet your memory network, details, gists, and schemas, trace transformation theory, reactivating old memories, and finally, why memory transforms.
Let's jump right into Section 1, the myth of static memory, and how we are shattering the standard consolidation theory.
You see, for decades, science really relied on what's called the standard consolidation theory. And this was the outdated belief that memories were laid down just once, acting as these static, unchangeable video files. The old idea was basically that your hippocampus binds a memory together initially, and then, over time, that exact same static file is simply handed off to the neocortex for permanent storage. Kind of like dropping a file in a dusty cabinet, right? But modern neuroscience shows us this is entirely wrong. Memories are absolutely not static files. They're incredibly malleable. The very nature of a memory actually changes at the neural level as time goes on.
Which brings us to Section 2, meet your memory network. Let's look at the actual anatomy of remembering.
To really get this, we have to look at how different regions of the brain handle completely different types of cues. It's like a highly coordinated team. Toward the back of the brain, the posterior hippocampus, or PHPC for short, handles all those rich, local perceptual details. Moving forward, the anterior hippocampus, the AHPC, grabs onto the broader gist of an event. And then way up near the front, the ventromedial prefrontal cortex, the VMPFC, manages these generic schemas. So your memory isn't just sitting in one magical spot. It's this incredibly distributed network spanning the long axis of the hippocampus and projecting all the way out into the neocortex.
Moving right along to Section 3, details, gists, and schemas. These are basically your 3 levels of memory resolution. It is honestly fascinating how perfectly mapped out these jobs are in the brain, moving from hyper-specific all the way up to broad, general rules. The posterior hippocampus is literally functionally connected to the visual and perceptual systems at the back of your brain, so it holds the details, the exact perceptual features. Then your anterior hippocampus serves as sort of the middleman, holding the gist, which are the global features of a specific event. And finally, the medial prefrontal cortex holds the schema, the general rules your brain has extracted from multiple experiences over time.
Okay, let's ground this a bit with our 10th birthday party analogy from earlier. The details processed by your posterior hippocampus, that's the exact visual of the chocolate frosting, or maybe your uncle's incredibly off-key singing. The gist, handled by your anterior hippocampus, is simply the fact that you had a gathering at mom's house. And the schema, housed up in the prefrontal cortex, well, that's your general knowledge of what a birthday party even is. You know that there will be cake, forced socializing, presents. It's an abstract template of the event.
This perfectly sets us up for Section 4, trace transformation theory, which explains how our memories physically change.
Let's watch how a memory dynamically ages over time. On day 1, right after an event actually happens, it's a highly detailed, context-specific trace locked firmly in that posterior hippocampus. But as time passes, say over a month, your brain starts to extract the gist, shifting its reliance over to the anterior hippocampus. By the time a year or more passes, the memory has literally physically transformed. Those unique, context-specific perceptual details, they often fade away, and what you are left with is a context-general schema, largely supported by the medial prefrontal cortex. The memory has physically migrated and completely changed its resolution. Crazy, right?
There's a quote from the research that perfectly summarizes this shift. It says, "Memories are dynamic, changing not only with age but also with experience as they interact with other memories and knowledge." So the absolutely crucial point here is that a memory isn't just decaying simply because it's getting older. Not at all. It's actively interacting with everything else you learn.
It's being updated, stripped of unnecessary details, and woven right into the fabric of your general knowledge.
All right, Section 5, reactivating old memories, or bringing high def back to life.
So what happens if, decades later, you suddenly smell the exact vanilla frosting from that 10th birthday cake? Can we bring that high-definition detail back to life? Well, the answer is a resounding yes, through this amazing process called reconsolidation. First, you encounter a highly specific reminder, like a scent or an old photo. That cue instantly bypasses the generalized schema and directly reactivates the original trace back in the posterior hippocampus. Suddenly, the memory becomes highly detailed again, but crucially, it becomes labile, which just means it's unstable and alterable. Finally, the memory undergoes reconsolidation, where it gets written back into your brain, often incorporating your current emotional state. This proves the original high-def details aren't necessarily gone forever, they sometimes just require the exact right key to unlock them.
And that brings us to our final part, Section 6, Why Memory Transforms, the evolutionary advantage of forgetting.
You might logically wonder, why on earth does the brain go through all this trouble to transform our memories, losing so much detail in the process, instead of just keeping the original high-definition video forever? Well, the ultimate answer is that memory transformation optimizes the brain to extract general rules for the future, rather than just hoarding useless past details. Think about it. Your brain is not a museum designed to perfectly document your past. It's an anticipation machine designed to keep you alive in the future. By pruning away those hyper-specific, one-off details, your brain creates highly efficient, overarching schemas. These schemas act as templates, allowing you to instantly understand and navigate totally new situations without having to process every little thing from scratch. Forgetting the exact pattern on a birthday cake literally frees up neural real estate so you can instantly recognize what a celebration is anywhere in the world.
So I want to leave you with this somewhat provocative thought. Is your most cherished childhood memory the actual, original event? Or is it just a beautifully transformed schema your brain has built and rebuilt over time? Every single time you recall it, you change it. Your memories are not the static past. They're living, breathing blueprints, constantly adapting to make you who you are today. Keep exploring, keep learning, and I'll catch you in the next explainer.